Good morning students, welcome to the chemistry class. Last class I have given the introduction to P block elements. So today I am going to commence 15th group elements. The 15th group elements are nitrogen, phosphorus, arsenic, antimony and bismuth. These are the symbols of P block element. These are the 15th group elements. So these are the symbols. Okay. Then the atomic numbers. So in the first year we are practiced up to third. In that, if we know second period elements atomic number, we can easily write the atomic number for remaining elements. So here the second period element is nitrogen. The atomic number is 7. Then the magic number for the P block element is 8, 18, 32, 32. These are the magic numbers for P block elements. It means that you need to add 8 to second period element. You will get third period elements atomic number. 8 plus 7, that is 15. Okay. Then next 18. Next element is 18. So for the third period element we need to add 18. Then this will be 8 plus 3, then 33. Okay. Then next 18 element, 18. Then add 18 to 33, fourth period element. 8 plus 3, 1, 11, then 51. Okay. Then next 32. So this is 32. So this will be 83. Okay, for bismuth atomic number is 83. Look here, nitrogen with atomic number 7, phosphorus 15, arsenic 33, then antimony 51 and bismuth is 83. Then, so how to remember the names of the 15th group elements? Names of the 15th group elements. In the last class also I have given the hints. So Neetu, Preetu, Aishwarya, sab beautiful. Like that also easily we can remember the 15th group element. Or Nepal, Pakistan, Australia, sab bindas. Okay, like this also you can remember the 15th group elements. Okay, then here these two, nitrogen and phosphorus, are non-metals. These two are non-metals in the periodic table, in the 15th group, and these arsenic and antimony are metalloid. Arsenic and antimony are metalloid, and bismuth is rare metal. Okay, bismuth is rare metal. Okay, so among these, nitrogen is gas. Nitrogen is gaseous in nature. This is non-metal. Nitrogen is non-metal. Phosphorus is solid non-metal. And arsenic and antimony are also solid. All these are solid. This is solid metal. Bismuth is solid metal. Okay. Then we know that the general electronic configuration for 15th group element. General is the general electronic configuration. This is the general electronic configuration for 15th group element. Here nitrogen, phosphorus, arsenic, antimony and bismuth. Okay, this is second period element. Sixth period element. Okay, and so that n is the principal quantum number. We know that n is the principal quantum number. Now the electronic configuration of each period is, the general electronic configuration for 15th group element is ns2 np3. Nitrogen is second period element, phosphorus is third period, arsenic is fourth period, and antimony is fifth period. Then bismuth is 6th period element. Okay, and here first noble gas is helium, then next neon. Okay, here first helium noble gas followed by 2s2 2p3, 2s2 2p3, then next here helium neon followed by 3 xenon 6s2 6p3. These are the electronic configuration. Okay, this is the general electronic configuration for 15th group element. It means noble gas followed by ns2 np3 is the general electronic configuration for p black element, 15th group element. So nitrogen is the second period element, so that helium noble gas configuration followed by 2s2 2p3. Next for phosphorus, it's a third period element. Neon, it's a noble gas followed by 3s2 3p3. Then arsenic, that is argon, fourth period element, that is argon followed by 4s2 4p3. Then antimony, fifth period, krypton followed by 5s2 5p3. Then bismuth, sixth period, xenon followed by 6s2 6p3. These are the condensed electronic configuration for these 15th group element. Here these are the outermost electronic configuration, electronic configuration. Okay, these are the valence electrons: 2s2 2p3, 3s2 3p3, 4s2 4p3, 5s2 5p3, 6s2 6p3. These are the outermost electrons which are. So next to occurrence. So the p black elements are nitrogen, phosphorus, arsenic, antimony and bismuth. Okay, so first nitrogen, it is in air 78% by volume, in atmosphere. (78% by volume in atmosphere), and in the form of protein, in plants and animals, in the form of protein in plants and animals. Earth crust, the Chile saltpeter, atomic molecular formula is NaNO3. Chile saltpeter. Then Indian saltpeter, that is KNO3. Okay, so these are the occurrence of nitrogen. 78% by volume in atmosphere, and it is available in the form of proteins, in the 78% by volume in the atmosphere, and it is available in the form of protein in plants and animals. Okay, and in the earth crust it is available in these two forms, Chile saltpeter and Indian saltpeter. Okay, that is NaNO3 and KNO3. The molecular formula is important. Chile saltpeter is NaNO3 and Indian saltpeter is KNO3. Okay, so next to phosphorus. Phosphorus, it is available in the form of apatite family, the minerals of apatite family. Apatite family general formula is Ca9PO4 6 CaX2. This is the general formula of apatite. In that fluorapatite, the molecular formula is Ca9PO4 6 CaF2, which is the part of rocks, phosphate rocks. phosphate rocks. Okay, so this is the part of rocks. Okay, so this is the part of rocks, and so that it is called phosphate rocks. Apatite family, that is fluorapatite. Fluorapatite Ca9PO4 CaF2. So that is the formula, molecular formula, and also phosphorus, it is present in bones. Phosphorus also present in bones and living cell and plant matter. So we know that actually phosphate, this phosphorus, it is available, it is present in our body, in living beings, in the form of phosphates. Phosphates, we know that. Okay, so in nucleotides and nucleosides we are studying about phosphates. So there phosphate is present in bones also present, in living cell also present, in plant matter it is also present. Next to, so these three, arsenic, antimony and bismuth, these are available in the form of sulfide minerals. These are available in the form of sulfide minerals. Okay, nitrogen, it is available in the atmosphere 78%, and in the earth crust, and also it is present in the form of protein, and this phosphorus, it is available in the form of minerals of apatite family. Which are apatite family? That is general formula is Ca9PO4 CaX2. It is the general formula. Among that, fluorapatite, that is Ca9PO4 CaF2 is the fluorapatite, which is the part of rocks, so that is called phosphate rocks. This is called phosphate rocks, and it is also present in bones, living cell, then plant matters. It is also present, okay, in the form of nucleotide and nucleosides we are observing in our body. Okay, so next to arsenic, antimony and bismuth, these are available in the form of sulfide minerals. So this is about the occurrence. Okay, next to oxidation state. So the general electronic configuration is NS2NP3 is the general electronic configuration for 15th group element. Among these, if they leaves 3 electrons, these are P3 electrons, they are going to take +3 oxidation state. By removing both S2 electron and P3 electrons, they are going to take +5 oxidation state. Both in S 2 electrons, in P 3 electrons, they are going to take +5 oxidation state. If I add up 3 electrons to p orbitals, because it is half filled electron, and so that we can add up 3 more electrons, maximum 6. So by adding 3, it is going to take -3 oxidation state. These are the common oxidation states. These are the common oxidation state of 15th group element. Okay, so look here. So here the elements of 15th group are nitrogen, phosphorus, arsenic, antimony and bismuth. Here all the elements, they exhibit all the 3. So here this is nitrogen, -3, -3, -3. So here actually this is a metal, bismuth is a metal. It is not give you -3 oxidation state, but it is more stable in +3 oxidation state. Okay, but it is it can give -3 oxidation state, but it is not at all stable. So here +3 they are stable, +5 also stable. Here also it is stable, and this also stable. +3, these are the common oxidation state. But look here, so here this is more stable. Bismuth, it is give you always +3 is more stable for bismuth, because bismuth is a metal. Generally metals are electropositive element. They are ready to donate an electron, they are not ready to accept an electron. So this is least stable. This least stable, actually it is not at all giving, okay, it is least stable bismuth, because it is a metal. Like S black elements, like S black elements, all metals, they are electropositive, they are ready to donate an electron instead of taking an electron. So look here, this is a non-metal, these are non-metals, they are ready more electronegative in nature, so that they are more stable in -3 oxidation state. So look here, for example, I will take NH3, okay, NH3, here this is -3 and here plus, okay. So this is -3 oxidation state, and like that PH3, this is minus oxidation state, okay. Similarly, all hydrates, in all hydrates, that is -3 oxidation state is more stable. So the stability of -3 oxidation state decreases, the stability decreases down the group. If you go down the group, the stability of -3 oxidation state decreases, it will decreases because the metallic property increases. Metals are electropositive in nature, they are not absorbing or attracting electrons, they are ready to donate an electrons. So bismuth is a metal, so that it is least stable in -3 oxidation state, but it is most stable in +3 oxidation state, okay. That is one. And here the +5 and +3, among this +3 and +5, +3 is more stable, +3 oxidation state is more stable. So also +5 decreases, +5, the stability of +5 decreases down the group due to inert pair effect, due to inert pair, due to inert pair effect, the stability of +5 oxidation state decreases, okay. And here due to inert pair effect, the bismuth is more stable in +3 oxidation state. Then what do you mean by inert pair? So this is the general electronic configuration. For example, if I take this one, NS2 NP3, among these, because of, okay, because s orbitals are more attracting towards, it is more shielding to nucleus, and these S2 electrons are not involving in chemical reaction. So what do you mean by inert pair effect? Inert pair effect, inert, due to inert pair effect, okay. So this bismuth is more stable in +3 oxidation state. What do you mean by inert pair effect? In this general electronic configuration, the S2 electrons are not involving in chemical reaction, only P electrons are involving in chemical reaction. The stability of +5 decreases down the group, but the stability of +3 increases down the group. If you go down the group, the stability of +3 oxidation state increases due to inert pair effect, due to inert pair effect. What do you mean by inert pair effect? The inert pair is in the S2 electrons are not involving in chemical reaction, only P electrons are involving in chemical reaction. The S2 electrons are tightly bounded to the nucleus, and that effect is called inert pair effect, so that they are going to take +3 oxidation state, okay. So this is about the common oxidation state is +3, +5 and +3, okay. Then they are going to give you disproportionate reaction. All these elements, they are more stable in a disproportionate reaction. For example, for nitrogen, if I take HNO3, so HNO2, it will give you HNO3 plus H2O plus 2NO. So look here, HNO2 give you HNO3 plus H2O plus 2NO. Here the oxidation state is +3. Here -4 +1, this is +3. Here 6, here +5. So here -2. The oxidation state is -2 here. So this is +3, +5, -2. So they are having variable oxidation states, and so that these are more stable. They are involving in disproportionate reaction, disproportionate redox reaction, okay. Increases atomic size, increases because here this is in the first shell 1s, this is 2s 2p, 3s 3p 3d, and the next to 4s, 4p, 4d, 4f. You see here the number of shells increases if you go down the group. We know that nitrogen is second period element, third period element, fourth period element, fifth and sixth period elements. These are bismuth is sixth period element. Okay, so this is second period, second, this is third, this is fourth, this is fifth, sixth period element. Okay, and if you go down the group, the number of shells also increases. Number of shells also increases, and so that if you go down the group, the size of an atom increases, and so that the atomic radii also increase. The increase in size from nitrogen to phosphorus is is very large due to 3d orbitals, due to d orbitals. D orbitals, it is very small, because and also electronegativity is very high for nitrogen compared to phosphorus. And here in the third period, 3d orbitals it will get added up, and so that there is a large increase in atomic size we are observing here. Here in case of antimony and bismuth, the less increase in atomic size, due to poor shielding, of d and f orbitals, due to poor shielding of d and f orbitals, we are not get expected increase in atomic size. We are not, because even though there is additional of d and f orbital, okay, there is no large increase in atomic size because of poor shielding of d and f orbital. D and f orbitals are not effectively shielding the nucleus, and so that the size of an atom sinks. Okay, there is a increase in atomic size, but not up to mark, not expected value we are not getting. And here there is a large increase in atomic size due to additional 3d orbitals. We knows that the ionization energy is inversely proportional to atomic size. As size of an atom increases, the ionization enthalpy decreases because of increase in screening effect, shielding effect, and decrease in effective nuclear charge. Okay, so look here, as we go down the group, ionization enthalpy decreases, due to increase in atomic size, Okay, so look here, if smaller the atom, okay, it is attracting, the electron cloud is attracting towards the nucleus. Okay, so if atom size is very high, very large, then the attracting power, the effective nuclear charge, ENC value decreases. Effective nuclear charge decreases, and shielding is increases. The shielding of nucleus increases, screening effect increases, effective nuclear charge decreases, and so that easily we can remove an electron from an outermost orbit very easily. Ionization enthalpy is energy required to remove an electron from an outermost isolated gaseous atom to an infinite distance. An infinite distance is called ionization enthalpy. So if a small atom is there, it is tightly bounded to the nucleus, electron is tightly bounded to the nucleus, and so that we need to supply more energy to remove that electron. But here for nitrogen, the ionization enthalpy is very high, it is more electronegative in nature and small in size, and if you go down the group, the size of an atom increases, and the number of shells also increases, so that screening effect also increases, so that effective nuclear charge decreases, and it is weakly bounded to the nucleus. This outermost electron is weakly bounded to the nucleus, and so that just by supplying a some energy we can remove this electron, and so ionization energy decreases down the group. And as we know that the first ionization energy, always we know that first ionization energy is less than the second ionization energy, and which is less than third ionization energy, okay, because here the effective nuclear charge 1 increases, and so that the first ionization energy is less compared to second ionization energy and third ionization energy. And here also in the general electronic configuration NS2 NP3, this NP3, this is completely filled. NS2 configuration, this is off filled electronic configuration, P3 configuration, okay. In p orbital maximum 6 electrons, but here only 3 electrons are present, so this is called off filled, okay, off filled electronic configuration. These are having off filled electronic configuration, these elements having extra stability, so that the ionization energy is more compared to previous group. The ionization energy of 15th group elements are very high compared to previous elements. Allotropes are different structural forms of same element which exhibit quite different physical and chemical properties. Okay, here nitrogen, it does not having allotropes. Phosphorus having number of allotropes, white, red, black, scarlet, alpha, beta, violet, like this. It is having a number of allotropes which are having okay, the structural forms of the same element which are having different physical and chemical behavior. And arsenic, it is having grey, yellow, black. Then antimony, it is having 2 allotropic forms which are highly explosive in nature, and bismuth, it does not having allotropes. Next to isotopes. What are isotopes? Okay, what are isotopes? They having same atomic number, and different atomic mass, So these are isotopes. So all elements are having isotopes. All 15th group elements having isotopes. Okay. Covalency of nitrogen, the covalency of nitrogen family. So here general formula, general electronic configuration is NS2 NP3. Number of bonds formed. The number of bonds formed. This depends on number of available orbitals surrounding the central atom. So how many number of orbitals are available surrounding the central atom, and depending on that number of bonds are going to form. Okay, that is covalency. So look here, in general electronic configuration, that is NS2 NP3, here one orbiter, in particularly this one, nitrogen, here 2s and 2p, only 4 orbitals are present, but here 3s, 3p and 3d orbitals are present in phosphorus. From here onwards, both d and f orbitals are also available. S, 4p, 4d and 4f orbitals are available. It means that here 5d, 5f, 6d, 6f orbitals are also available in these 3. Okay. So look here, in general, in particularly in nitrogen, only 3 bonds it is going to form here. Okay. Then next, because it is not having any d orbitals are not there, d orbitals are not available, and so that it can't able to shift this s electrons to next upcoming orbital, and so that it can able to form only maximum 3 bonds here. But phosphorus, it is having a vacant d orbital, so that it can shift s electrons to d orbitals. For example, nitrogen 1s2, 2s2, 2p3. Then phosphorus 1s2, 2s2, 2p3, 2p6, 3s2, 3p3 and 3d vacant 3d orbitals are available. So here what will happen? So here for shifting, for bonding, 1 2s 2p, this is 2 electrons, it will be here 1 2 3 in case of nitrogen. In case of nitrogen, so there is no bond formation, it has to shift here, but no available d orbitals in nitrogen. But in case of phosphorus, okay, so here vacant d orbitals are there, 3s orbitals to d orbitals, this is p orbitals, so d orbitals, 5 d orbitals, 1 2 3 4 5. So it can shift this 3s2 or 3s2 electrons to here 1, and thereby it can extend its covalency. And here it is 5, here also it is 5, and here also it is 5, but here it is bismuth, it is 3 because of inert pair effect. Inert pair effect. Because of inert pair effect, bismuth covalency is 3. Okay. So but phosphorus, it can shift, and so that it can form 5 bonds, even arsenic, even antimony. Then this is the covalency. But in the exam they will ask what is the maximum covalency. Covalency is different, oxidation state is different. Maximum covalency of nitrogen family. Maximum covalency of nitrogen family. Look here, this covalency. So here covalency, so that is number of bonds formed surrounding this atom. So here because only 3 orbitals are available for bonding. Next to phosphorus, it can extend up to 5. It can form 3 or it can extend up to 5. Then all these 3 similarly, but bismuth, it can form only 3 bonds because of inert pair effect. But in the exam they will ask what is the maximum covalency. The maximum covalency of nitrogen is 4. The maximum covalency of nitrogen is 4. For phosphorus it is 6, and even antimony it is 6, and Sb also it is 6. Okay, the maximum covalency for nitrogen it is 6. You look here, the 2s2 2p3. Okay, here nitrogen, it is having a lone pair of electron, lone pair of electron, and here these are the 3 bonds, NH3. Okay, so here by donating this one, by donating a pair of electron to other, then it can going to form one more bond. For example, NH4 plus, here it can form nitrogen H. Maximum covalency by donating a pair of electron to other elements, it can form maximum 4 bonds. The maximum covalency is 4, but covalency of nitrogen in general, that is 3. Okay, maximum covalency is 3. Phosphorus also, for example, in case of P6, in case of PF6 minus, here the covalency is 6. Okay, so look here, for phosphorus, okay, so this is 3s2 3p3. Okay, so here it can extend this one to 3d, just 3d 0 I will write it. So here this is p, then this is d, 1 2 3 4 5. Okay, this is 1 2 3 4 5. This is 5 bonds. Then 6, but sixth bond by accepting a pair of electrons, pair of electron, so it is going to form 6, covalency is 6, it is going to form covalency 6. Okay, by accepting a pair of electron, because there is available of vacant d orbitals, availability of vacant d orbitals, vacant orbitals are available, and so that it can accept, it can receive 2 electrons and thereby it can form 6 covalency octahedral structure. Okay. So that similarly on arsenic as well as bismuth, they are going to form maximum 6 bonds surrounding them because of the availability of d orbitals. Okay. So you should read very carefully the questions. The maximum covalency is 4, 6, 6, 6. Then oxidation number is +3 +5, +3 +5 -3. Okay. Covalency is different from oxidation state. Covalency is formation of bonds surrounding that atom. Maximum these can form 4 bond by nitrogen and 6 bond from these, and bismuth is only 3. Okay, because of inert pair effect. The s electrons are not involving in chemical reaction. Okay, so this is about covalency. Next to atomicity of nitrogen family. So what do you mean by atomicity? The total number of atoms that constitute a molecule. So here nitrogen, it is exist in N2 form, nitrogen dimer. Okay, phosphorus, it is in form of P4, and arsenic AS4. Okay, then Sb, okay, Sb4, then bismuth, that is metallic bonding, metallic bonding. So look here. So here it is available in dimer form. 2 atoms are combining. In case of phosphorus, P4, 4 atoms combined together and they are bonded themselves and they are going to form molecule. So that is called catenation or atomicity. Then arsenic AS4, then Sb4. Bismuth, it is going to form metallic bonding because it is a metal. Okay, so here this is important. So they are going to form molecule through covalent bond. But here this is metallic bonding. It is going to form metallic bonding. So here in nitrogen, it is going to form only dimer, but it is not exist in form of N4. N4 form is not existing, but only it is going to form N2 form. That is, okay, generally we says that d orbitals are absent, so that it does not forms N4, but it will be available in the form of N2. That is wrong actually. So due to smaller size nitrogen, okay, nitrogen due to small size and high electronegativity, it is going to form N2 forms. Look here. So nitrogen, so these are lone pair of electron. What will happens? This we knows that repulsion between lone pair is very high. Repulsion between lone pair is very high, and so that the single bond becomes weak in case of nitrogen. Single bond becomes weak compared to PP bond. But in phosphorus, the atom is larger. The atom is so larger. Here, this is 2p, and 2s. Here, 3p orbitals. Okay, 3p orbitals, and the molecule is larger compared to nitrogen. Then repulsion decreases, and so that N single bond NN bond is single bond N is weaker compared to PP single bond. And so what will happen? This is weak bond, but they are very small in size. These are small in size and high electronegativity value, and they are having same size. And so what will happen? This 2p overlapping to form pi bonds, pi bond to form pi bond is more effective, it is more effective. The pi bond is more effective. More overlapping we are observing in case of nitrogen. Overlapping is very high, but in case of p orbital, the size is very large, and overlapping is less effective. Overlapping is not possible, okay, less effective. And so that here it is nitrogen, it is going to form N triple bond N. Nitrogen, it is going to form N triple bond N. And this pp overlapping, it is more effective in case of nitrogen. They are very more electronegative, and the size is very small, so that they are very near to each other, and overlapping is more effective, and so that they are going to form N triple bond N. In case of phosphorus, p overlapping is very less effective, and so that they are going for polymerization to form P4, okay. So here this is not due to, because N2, it is nitrogen, it is going to exist in form of N2, but it does not exist in the form of N4. That is not due to the absence of d orbitals, but actually that is the repulsion between lone pair and lone pair is very high, and nitrogen is very small in size and more high electronegativity value, and so that the single bond is very weak, okay. The single bond is very weak, and so that atomicity decreases in case of nitrogen. For polymerization or for atomicity or for catenation, so single bond strength is strong, catenation is directly proportional to strength of single bond. This in catenation, the strength of single bond increases, the polymerization increases. Here the catenation property increases down the group due to increase in strength of single bond. If we come top to bottom, in nitrogen single bond is weak compared to pp single bond, okay. The single bond strength increases, so that the catenation property also increases, and so that nitrogen exists only in dimer form, not in N4. But phosphorus, arsenic and antimony, these are existing E4 forms because of increase in single bond strength, and so that they are going to form polymerization. And bismuth, it is metallic in nature, it is going to form metallic bond, not it is going to form covalent bond. Bismuth not forming covalent bond, it is going to form metallic bonding, okay. In case of nitrogen, we are observing p pi bonds, okay, only p pi bonds because of the absence of d orbitals. But here we are observing both p pi and d pi overlapping phosphorus, okay. If you go down the group, we are going to observe d pi bonds also, overlapping also we are observing. Look here. So in case of nitrogen, we are having 2s2 2p3, okay. So only p orbitals are available, in p orbitals unpaired electrons available, and so that it is going to form only p pi bonds. Nitrogen, it is going to form only p pi bonds. But in case of phosphorus, it is going to form p pi d pi also. For example, you take oxygen, so that is this is in excited state, this is 1, then this is p, 1 2 3, this is 3p 3s, then d, 1 2 3 4 5, okay, here d, okay. So here look here, this is d pi. So for example, p double bond O, this is Cl, so it is going to form p pi. In this compound, it is going to form p pi d pi bonds. In case of arsenic and bismuth, so here As C6 H5 and phosphorus C2 H5, these two acts as a ligand. And with the transition elements, they are going to form d pi bonds. D pi bonds. With the transition, with the 3D elements, with the D block elements, they are going to form d pi bonds, where arsenic C6 H5 and P C2H5, here these two acting as a ligand, they are going to form d pi bonds. But here in this compound it is going to form p pi d pi, but nitrogen it is going to form only p pi bonds. Elements like this nitrogen, it is going to form multiple bonds with carbon oxygen. Okay, so for example N triple bond C and NO, like this, it is going to form 2 pi bonds with carbon and oxygen, because they are having almost same size and almost similar electronegativity value, and so that it is going to form p pi bonds. So look here the melting point and boiling point. You see here the melting point. Okay, this is the melting point of nitrogen, that is minus 209.71 degrees centigrade. Then for phosphorus it is 44.3 degrees centigrade. Then for arsenic it is 817 degrees centigrade. Okay, and then for antimony it is 630.89 degrees centigrade. For bismuth it is 271.5 degree centigrade. Look here, actually as we go down the group, the atomic mass increases and metallic character also increases. The melting point of 15th group element should increase, but here up to from nitrogen to arsenic it is increases. The melting point increases from nitrogen, phosphorus, arsenic, antimony, and nitrogen to arsenic. The melting point increases, but here onwards it is decreases. Melting point decreases from arsenic onwards, from antimony to bismuth. That is due to inert pair effect. Inert pair effect, and also it depends on packing efficiency. Okay, so here you see from nitrogen to arsenic the covalency increases. From here the melting point increases up to arsenic, once again it is decreases. Okay, so next to boiling point. As we go down the group, the boiling point of 15th group element increases. As we go from nitrogen to phosphorus, arsenic, antimony and bismuth, the boiling point increases. For nitrogen it is boiling point is minus 195.6 degrees centigrade. Then for phosphorus it is 280 degrees centigrade. For arsenic it is 613 degrees centigrade. For antimony it is 1635 degrees centigrade. For bismuth it is 1560 degrees centigrade. As we move down the group, the boiling point increases. Okay, the boiling point increases. We know that this boiling point depends on, first point depends on van der Waals force of attraction. Okay, then it depends on molecular mass. Okay, the boiling point mainly depends on van der Waals force of attraction. This is gas, we know that nitrogen is a gas. So weak van der Waals force of attraction we are observing here. Then has moved down the group, the molar mass increases, and so that the boiling point is also increases. So as the mass of an atom is increases, then energy required to lift from liquid to gas, okay, gas, it takes more energy, so that the boiling point decreases as molar mass of 15th group element increases. And also here this depends on van der Waals force of attraction, the force of attraction, okay, force of attraction between the atoms. So here the force of attraction increases, the metallic bonding here force of attraction is more, and so that bismuth having more boiling point, okay. So like this, if you go down the group, melting point increases up to arsenic, but it is decreases from antimony to bismuth due to inert, mainly due to inert pair effect. Then here boiling point it is decreases, boiling point it is increases down the group. So this depends on van der Waals force of attraction as well as molar mass. Down the group molar mass increases, so boiling point also increases, okay. So to this I am going to stop the class. Then in the next class I am going to discuss about reactions with hydrogen, oxygen and halogens and dinitrogen, okay. Thank you, enjoy the day, thank you.